Good day, guys. So today we'll be talking about PCB design basics, and we'll be looking at four various technologies on the PCB design. We'll be looking at the tracks, we'll be looking at the vias, we'll also be looking at the clearances and the pad sizes, and how this all affects you when you're designing a PCB. And we'll also look at how to design a PCB the proper way using this to get better outcome. So let's move. So the tracks are either called tracks or traces. We either call them tracks or traces. So if you hear tracks or you hear traces, we're actually talking about the same thing. So what did they do? They carry electrical signals and power across the board. This is just like the track. It carries electrical signal and power across the board. And I'll also be showing you guys a board being designed by one of my students. We'll be using that for references, and I'll show you guys what the tracks look like. You get, so these are the tracks. You get, they carry electrical signal from one point of the board to the other. They are actually called copper traces also. Copper traces used to move signal from one point to the other, used to move power from one point to the other on your PCB board. So the next one I have here, that wider tracks carry more current and reduce heat. Okay, this when dealing with some power designs, or you're dealing with the power section of your board, it's always good to use wider tracks or wider traces for that point, so that it can actually contain the amount of current that is passing through that line. So though these have a particular calculation that you can do to get the exact track width on that. So we also have use to route between components logically. So this is what tracks do, or traces. They are used to route between components logically. So you route from one component pad to the other component pad. That is a function of the track. So we'll have some design notes here. As I said earlier on, higher current equals to wider track. So when your system is dealing with some high current, when you're using about 2 amps, 3 amps, 4 amps, you won't use the track width that you use for about 40 milliamps of current to contain about 5 amp of current. You can either have a short circuit on your board, or you can get your board burnt off. So we also have here that shorter traces reduces noise. This in terms of when you're dealing with some critical signal or some high speed design, when it's always good, or some RF design, it's always good to use shorter traces, because it can reduce noise drastically on your board. It can reduce noise drastically on your board. And I also have here that high-speed signals may need controlled impedance. Okay, so controlled impedance is making sure that the impedance from the driver, which is the your IC or any of your peripheral components, to the receiver, the track within then has the same impedance as the input going to the output. So that's for track width. Then the next one is vias. So vias, what are vias? Plated holes connecting copper between layers. I'll show you guys an example. So this is via. What via does is via actually bridges different layer together. You can use it to make connection between your top layer and your bottom layer. So we have different kinds of PCB boards. We have the single layer PCB board, we have the double layer PCB board, and we also have the multi-layer PCB board. So the function of the via in that aspect is it actually helps you to establish connection between your top layer and your bottom layer, or your top layer and your inner layer, or it just helps you establish connection between any kinds of layer at all. Though we have different kinds of vias, we have the micro vias, we have the blind and very buried vias, we also have the through hole vias. The through hole vias is mostly used in some basic application. Yes, through hole vias is used in some basic application. Let's move further. Allows routing signals when top and bottom layers are congested. That's what I say. Then supports multi-layer power distribution. Then we have via design notes. Keep via count balanced to avoid complexity. Then avoid placing vias on pads unless needed. avoid placing veers on parts unless needed. What this means is, let me take a veer here. So this is just something like this. Avoid placing veers. So this is my veer. Avoid placing veers on parts like this. So my veer is actually on this point. So one reason for this is sometimes during manufacturing, they can have some it can actually generate some errors, or if you want to solder your board and all that manually, it can generate some errors. But if you're doing this, it can also increase the cost of your board because they might need to add resin on your board to make everything well. But when you're designing some complex board using BGA packages and some advanced board, we also have what we call VIA pad. So you can always use that. But this is just for informational purposes. Then use stitching veers to improve grounding. Like what I have here on the image here is actually stitching veers. These are all stitching veers. So I'll move to the next one, clearances. So clearance equals to space between copper futures. This is just space between copper. It can be your tracks. So it's just like space between two tracks, space between two traces, the space between two veers. And your clearance is actually important. And to know the minimum amount of clearance you need to put on your design, you always need to check from your manufacturer. You need to check from your manufacturer and ask them, okay, check their websites, check for their capabilities. Sometimes you can also send them an email to get their capabilities and what they can handle. You get, so it just, the clearance is just something like this. So this space between these two copper layer, these traces, is actually the clearance for this. Sometimes they might tell you that the minimum amount of clearance that you can use is 0.1 mils, sorry, 0.1 millimeter. So you need to always consider that when doing your design. Always consider clearance between two copper layers, sorry, between two copper traces. Always consider clearance between two vias also. So this line and this line, always consider clearance between all those stuff. And the clearance is always stated on the manufacturer's capability and depending on your own design application also. So we move further. I have here protect against short circuit and bridging. This is what I said. It protects against short circuit and bridging. If two copper traces of different nets meet together, you actually have a short circuit on your board and the signals will bridge and your board won't work appropriately as intended. Then defined by PCB manufacturers rules, what I stated earlier on. Then clearance design notes, higher voltage requires larger clearance, tight spacing increases risk of defects. Follow design rules check always. Follow design rules check always. When done with your PCB layout, it's always good to follow your design rules check and to confirm where errors are. And the design rule check also states if there is any clearance violation so that you can solve that before going to your manufacturer. Then the last one we'll be looking at is actually the pad sizes. So what is this? Copper landing spot for soldering component. Just this, the pad size. The pad size is actually how the physical, I can call it leg or physical shape of the board would be, the physical leg of the board would be on the PCB board. So these are pad. This is a pad. Okay, this is the pad for this microcontroller and this is the pad for this component. So it has about 4 parts, 1, 2, 3, 4. This is the pad for this. I guess this is a transistor. It has about 3 parts, 1, 2, 3. You get, so these are where the components will fit on top. I can also show you guys the 3D view of this. So this is the 3D view. This was the microcontroller I showed you guys. Then this is the transistor and all the other components. So the pad is actually where they fit into so that it can be soldered or so that it can actually establish firm connection on your PCB board. Okay, so provide mechanical anchoring and electrical contacts. Yes, then must match components footprint. Make sure it matches your component footprint and always confirm your component footprint from your datasheet or the manufacturer's datasheet. Then pad design notes. Larger pad improves solder reliability. Avoid extremely small pads, weak joints. Then through-hole pads must meet drill tolerances. These are vital informations. Then just putting it all together, tracks route signals and power, and they also connect components together electrically. Then vias establish vertical routing, and it also helps to establish connection between different layers of your PCB board. Then clearance ensures safety and manufacturability, and it also helps that there's no issue on your board. Then part sizing guarantees solid solder connection. So this is all for today, guys. Thank you, guys. I want you guys to subscribe and like. If there are any errors or anything you feel that wasn't said right or well on the video, you can always comment below, and also comment below the topics you want to be seeing. Thank you, guys.